We now come to the third part of the course, which is deep foundations. And the first thing we're going to talk about is driven piles, and this is a subject for me that's very much close to the heart. I've been involved with driven piles virtually my entire working career, and of course those that went before me were involved with it. My family business developed the pile driving equipment that basically sustained it in the late 1880s, although actually it had done some before that, actually dating back maybe to the 1870s. But the current line that is most people associate with Vulcan was developed in the late 1880s and has continued through all the history of the company, and is still being maintained and updated, and well, not it's updated but maintained. It's an interesting type of foundation. It looks very simple. It is not, and I'm going to try to make it as simple as possible, and try to give you, in today's lecture, is a little bit kind of the lay of the land sort of thing. I've also done some other writing about it, and most of my research has been involved with driven piles, including the fine element research I did in the past decade. So, with all that, let's get started. By the way, this photo was taken it actually was in the Persian Gulf in the early 1970s, 73 I believe, and at the offshore oil platforms. Driving piles for an offshore oil platform. Okay, I think maybe since this whole section is on deep foundations, it probably would be a good idea to stop and ask the question, why do we have deep foundations? And I think maybe the easiest way to answer that question is to ask the question, what are shallow foundations' strengths and what are shallow foundations' weaknesses? The strong point of shallow foundations is they're generally economical. They have, however, several, and in reasonably competent soils, and if you take into account their settlement, they generally do okay. If those conditions are not present, if you have, and of course for compressive loads, they're not particularly, they can sustain some lateral loading but not a lot, and you're in situations where you need lateral support, where you need tension loading, where you need the things that shallow foundations cannot produce, then you can turn to deep foundations. Now, there are foundations which are probably best referred to as intermediate foundations, soil columns and that sort of thing. I'm not going to spend any time on intermediate foundations. The different types of foundations that have been developed are a pretty broad spectrum of engineering designs, and it would take a lot more than just an introductory course like this one to go into them. But basically, as this describes, the basic purpose of deep foundations is to transfer the load from either an unsuitable bearing area to a suitable bearing area. That's the primary purpose. Generally speaking, if we have decently competent soils at the surface, shallow foundations will usually get the job done. If we don't, and that's very common in situations, particularly in coastal applications, marine applications, then we need to lengthen the foundation basically to get it down to where we can actually find the types of soils or rock even that will support our structure. And that's the basic purpose of foundation. It's not the only one. Again, with tension loads, with lateral loads, if you have those even in competent soil, sometimes you're forced to use some type of deep foundation. or an intermediate foundation. So, and in a pictorial sense, you have these. You have the classic. Let's get down to competent layers is in this one. This A. In some cases, it is impossible to get to competent layers. They're just too deep. And so, therefore, what you do is you get to as much poured soft soils as you get enough soft soils, and you essentially engage enough soft soils, and you can make a substitute for that. That's particularly true in areas like New Orleans, South Louisiana, where you don't have bedrock can be very, very, or any kind of competent layer can be very deep, and those are along the side. When you get a lot of shaft friction, resistance along the side. We're going to get into that. You also have tension loads and lateral loads, C and D, which are a very strong reason for deep foundations. Many structures rely on the lateral resistance of foundations to stay put. Probably one well-known would be like a transmission tower, where you have wind loads, ocean loads for offshore platforms, or for that matter, these monopiles, sea-based monopiles, have large lateral loads, and those require deep foundations. You also have, if you have any kind of, and again, the E and F are sort of extensions of C and D, where you have lateral loads or moments that require the foundation needs more support. One alternative to deep foundations, I mentioned the transmission towers in passing, is if you are founding transmission towers on rock or whatnot, you can sometimes ballast them. In other words, put enough weight in the foundation which will basically resist your lateral loading. That's very common with transmission towers, and particularly in this part of the country. G is interesting because scour, usually if a bridge foundation fails, in most cases you're looking at least to some degree a scour failure. It's very seldom that bridge, usually, well, let me back up what scour is. Scour is the action of usually water that erodes the soil around a foundation and reduces the amount of area of the soil that the soil surrounding the foundation can be used to resist the loads, mostly lateral loads. And scour can be very, very dangerous. Like I said, most major bridge washouts, if the foundation goes, which is generally the case, you're looking at a scour load. This is a major issue in bridge design, even with very small bridges. If you have a bridge where, at one time you had scour, you had a creek or riverbed at a certain level and it's gone down because of scour, your ability of the foundation to laterally resist the loads has been compromised significantly and needs to be addressed. Liquefaction, susceptible, H, earthquakes. Earthquakes are very prone to liquefy the soils, either through thixotropy, and I'll talk about that maybe later with vibratory hammers, or with raising the pore water pressures in soils. And with that, you get lateral loads that require resistance using a foundation. Very often, if you see seismic retrofits, the common way of attacking those is to install very large, usually steel. Sometimes they'll use large drill shafts, but very often they'll use steel, what we call caissons, or just in the lingo, cans, very large steel pipe piles. And those have very high moments of inertia, and they are able to withstand the loads, the lateral loads, well, because basically in lateral loading, a pile is loaded like a beam, just like you see with sheet piling and everything else. So those situations are becoming, well, in places like California, they've been an issue for years. We're seeing in the last 15, 20 years more interest in what the new mandrel fault might do, and we're seeing more seismic retrofits in and around the new mandrel fault, and the states around the new mandrel fault are having to deal with this issue. It's if I had to pick the largest emerging topic in my career in geotechnical engineering, it would definitely be seismic loading. And we had a little bit of introduction to seismic loading with Mononobe Okabe and soil mechanics, but that was a very simple. The deep foundation, sometimes things get more complicated than that. We have other types of loads. We have impact loads. That's what I is all about. In the late 1970s, a freighter hit the Sunshine Skyway Bridge. It collapsed. Many people died in that, and they were required to replace it. And I think that really drove home the need for impact resistance for bridges. And frequently, as that diagram shows, you have a pile system which is independent of what's supporting the pier or whatnot in the impact system. Impacts or systems for ships are not new. You've got fender systems and whatnot for docks. This is a whole different, where either through bad seamanship or inclement weather or other factors, you have a ship impacts a bridge pier or some other structure, and we frequently design for those situations, design entirely separate structures to resist those. Future excavation, if you're anticipating a future excavation, you may need a deep foundation. And last but not least, swelling soil. And we're going to get into the issue of swelling soils towards the end of the course. Swelling soils can be very, very destructive. Very destructive. And you'll see what I'm talking about when we get down there. As I said before, one of the main reasons why we use foundations, deep foundations, is to resist loads that otherwise could not be resisted. Either compression loads in low competency soils, soft soils, loose soils, or tension loads or compression loads to horizontal loads in soft soils. These are prime applications for deep foundations. There are many types of deep foundations. Again, this is another chart similar to what we did with retaining walls. Each of these types of foundations has its application, and it's important to understand one thing that, I think this is, every deep foundation has its best application. And I think this was illustrated in the late 1970s. We were involved in the installation of driven piles under a power plant they were building northwest of Houston. And so we went out there, and they were having no end of problems getting the piles in the ground. And the Montmorillonite clay just would not give up. And basically, the individual who was doing some of our sales work, who was a very competent civil engineer, and I think he had actually worked on the Panama Canal, said that this place doesn't need driven piles. really is true. In soils like that, you'd be better off either with drill shafts, which is one reason why Texas Department of Transportation uses so many of them, or maybe none at all, depending upon the if they really sat down and thought this design through. Not every deep foundation has its application, and the key to a successful design is understanding what your options are and how to apply the different types of foundations to what you're doing. We're only going to consider, and as you said, there are many of them, and then we're only going to consider two of them. The first one is driven piles, which we're going to talk about shortly, and drill shafts and auger cast piles. Auger cast piles and drill shafts are basically designed in the same way, but their installation procedure is very different. So we're going to discuss that when we get there. We're going to do driven, well, let me just outline. We're going to do driven piles first, and then we're going to get into drill shafts and auger cast piles and those things. We've gone through the rationale for deep foundations in general. We're going to do this particular, I was going to talk about the overview of driven piles and pile driving. Most students who take this course are completely unfamiliar. I actually had a few years back a student who had actually worked for a construction company that did pile driving, not only just regular driven piles, but also sheet pile walls as well, but that's exceptional. Some of my non-traditional students have experience in this. Most of my students, non-traditional or other traditional, don't. So that's the reason why we're going to do this. We're going to talk about the design process this time, and then we're going to get into the equipment as well this time, and we're going to get into the factor of safety considerations. In the next two lectures, we'll talk about the single pile static design, the designs of pile, and then after that, we're going to talk about the bearing capacity, and after that, we're going to talk about the settlement calculations and the design of pile groups together. And down drag. I'm going to give a brief discussion of down drag, very brief. And later on, we'll talk about the static and dynamic load testing of piles. This is a rearrangement from the way I've done it in the past. Normally, I've run all these things together. I've decided to do it separately this time. A driven pile is a long, slender, prefabricated structural member driven by impact or vibration, or occasionally they're jacked. Occasionally they are jacked into the ground. That's pretty much it. That particular photo here shows a hammer driving a steel pipe pile, which we're going to talk about for an offshore oil platform. And it's driving them on a batter. And the reason why it's driving on the batter is most offshore platforms, as opposed to, say, what you see now with the offshore wind farms, are tapered. The design is kind of like a transmission tower. It's tapered. It's wide at the bottom. It gets narrow at the top. So therefore, the piles that support them, and they're actually driven through the legs of the platform, are battered or angled likewise. We'll talk about why we do that. There's a couple of reasons from a foundation standpoint. Well, that's a good idea. The taper in the design and the structure is largely due to the bending moment requirements of the structure, which are the greatest, like any other cantilever, it's the greatest of the bottom. You remember when we were doing retaining walls, and that nice, and many of the retaining walls, the gravity walls we had were thicker at the bottom than they were at the top, and that's why. And same thing here. Driven piles are the oldest form of deep foundation in existence, and all the ancient civilizations, the Greeks, Romans, the Chinese, and all the civilizations of the Middle East, the Persians, Babylonians, the Assyrians, and all of those, and all those that came after, have used driven piles to support structures in poor soils. driving in for thousands of years. Driven piles were installed. They were wood, exclusively wood, and they were basically done using a rig like you're looking at, where you actually pulled up the driver by hand, sometimes literally by hand, either by hand, or if you had a really sophisticated operator, you might have a few mules or horses to help out, and then it was just pulled up and drop, and then pulled up and drop, and then pulled up and drop. That's the drop hammers. You still see them, but they're not, obviously not pulled up by hand anymore. We use a crane for that. One of the most celebrated examples from the ancient world is Caesar's bridge over the Rhine, which he built when his conquest of Gaul decided to go over to Germany. It was built in a span of 10 days, and the batter piles were used. He drove batter piles to take the lateral loads of the river. The Rhine River, like any other river, particularly one as large as the Rhine, you have a fairly substantial current. You have flow of water against the the bridge. That's what creates a lateral load. Now, the quick and dirty way of dealing with lateral loads is something called batter piles. You'll notice here you have these piles at an angle, and the piles are at an angle basically is an attempt to turn a lateral load into an axial. And in other words, instead of having just a beam load, the load is transferred through here and down this way. That is still used. Those of you who have been to Florida, and who hasn't been to Florida, will find that you'll see the same thing. Many of the bridges down there have angled piles. Well, that's why they're trying to support the lateral loads on the bridge. Again, originally hammers were drop hammers. It was not until the 19th century that the use of forging hammers, and forging hammers are used to beat metal into not only into shapes but to alter its properties as well, were adapted by a Scotsman named James Naismith to driving piles, and his designs were made it over to the U.S. and were adapted in various ways, and ultimately ended up, the first steam hammers under Vulcan, and other manufacturers like MKT and whatnot made steam or air hammers as well today. Steam, except for offshore, was pretty much a done deal by World War II. The transition took place between the two world wars, between steam and air. Many of the rigs that were used in those days were either skid rigs, I'd say rotating skid rigs. A lot of them weren't even rotating skid rigs. They were just skid rigs where you just drug them along the ground where you were going. And crawler, and later on you had crawler mounted rigs. A lot of the pile driving is done today using crane mounted rigs. In fact, I would say a majority of it. There are still applications for dedicated pile driving rigs. If you do enough of it, it makes sense to dedicate one. And there are also the adaptation, and I've been involved with this personally, in using excavators to drive pile. And we'll see some examples of that on video here during the presentation. Piles, up to then it was all wood. Steel and concrete piles came in towards the end of the 19th century. H piles were adapted from I-beams and to address these scour issues, and pipe piles. Precast concrete piles were first used in 1897 by François Hennevik, and then A.A. Raymond came up with used these piles and pre-stressed concrete piles to build the Raymond Concrete Pile Company. which was at one time the largest pile driving organization in the world, and was the source of many advanced developments. That brief history, it's really brief, was used for, it kind of gives an overview of how we got where we are. There are type of piles used are timber piles and steel piles, concretes and other types. We're going to talk about all of those. What you select depends on the loads, the diameter, the type of soil you're driving into, the availability, and the durability in a specific environment and the driving conditions. For example, in this region, steel H-beams driven to rock are the most common driven piles you have in this area. In a place like Florida, you have more of your concrete piles. You're mostly pre-stressed, either square, or for your larger jobs, you have your cylindrical piles. Timber piles are the oldest type of pile in use. Mostly today they are either southern pine or Douglas fir. To be honest, timber piles have a much greater, have stood the test of time better than I thought they would, because of, and I've talked with retaining walls about creosote and its impact, and of course marine borers and those things. Nevertheless, in spite of those, timber piles are still used in a surprisingly large amount of jobs. I talked about pile compaction, which used several thousand timber piles in just down the road in Dalton. So timber piles are still very much a viable deep foundation type, even though they are limited in their length and they're limited in their capacity. They are still very extensively used. Steel piles were first developed in the 1890s. As I said, they can be driven through very hard soils and carry very large loads. They are especially used for tension and uplift loads. Steel is fine in tension. They're easy to splice net onto. Sometimes, in this particular photo, shows an offshore application where they actually just weld. They drive one segment and they weld another one. They add one to it and they weld it. Usually, welding is a way that you drive steel piles segmentally. Some fancier, offshore, they had breech block connectors and that sort of thing. But usually, welding is the easiest, expensive compared to other piles, and they may be subject to corrosion depending upon the soil and water conditions. For most freshwater table applications, corrosion is not a big issue with steel piling. The biggest place you see problems with steel piling, and one reason why you see so much concrete piling in places like Florida, is because you get into the worst place for corrosion to take place is the splash zone. The splash zone basically is the area between low tide and high tide in salt water. And so you have a situation where that area is most subject to corrosion and deterioration. You see the same thing with wood piles as well. Also, the further south you go, the warmer the water gets. The warmer the water gets, the more corrosion becomes a problem. H-piles were developed from wide flange beams. The flanges of webs are on equal thickness, and they're often used as end-bearing piles in rock, as I've mentioned before. H-piles are very versatile. They don't require a lot of once you drive them, that's it. They can handle. They're easy to handle, and they the only thing you got to watch for, if you use them for lateral loads, the moment of inertia in one direction is not the same as the others. This is an H-pile chart, some Skyline steel, the same place that the that my other charts came from for sheet piling. Notice that it has traditionally, until about maybe 10 years ago, all H-beams went up to 14 inch and stopped. They now do have 16, 18 inch H-beams. And they're not that commonly used because I think it's a matter of getting them in the spec, and that's always a slow process. But they're made in different weights and sizes and whatnot. Pipe piles, as the name implies, are basically a pipe. They can be spiral welded, or but I remember for offshore, those pipes, many times they were just rolled and seam and just straight seam welded. Spiral welding, you roll them out and then you weld them along a spiral. They are made with all kinds of the materials are showing here. And by the way, this is one of the things that I'll mention. I think this comes from your book, is the fact that your lower grades of piling, specifically A36, is pretty much out the window. You almost never see. They haven't rolled A36 in a long time in H-piles. Most of the time, they are your dash 50 or 60 grades, and pipes very much the same. The lower yield stresses are pretty much out. So, I did just a note. This slide actually came from Mexico, and it shows how they're applied in an offshore application, where I might note that the wall thickness of the pipe changes. It's thickest at the mud line because the shear loads and the bending moments are greatest at the mud line, and then it decreases up and down. So that's an interesting way. Another interesting thing about pipe piles, you can have the same size of pipe pile. Pipe pile can have one size, but it can have different wall thicknesses depending upon the loading at that area. Concrete piles are either precast or pre-stressed. Precast pretty much, describes it all. They put the rebar in, they pour it. Outside of North America, precast piles are reasonably common. Here, you almost never see them. Usually are pre-stressed, where you've got cables which are tensioned before the concrete is poured. Pre-stressed concrete piles, whether they be square or cylinder, are pretty much dominate that in the United States. Square concrete piles have a square plane form. By the way, unlike other types of concrete structures, square concrete piles in generally have a fairly fixed. Now, we're starting to see this loosen up a little bit, but traditionally, concrete piles have a fairly limited number of configurations. And I've got tables for those configurations. That's beginning to loosen up as people are designing designer square and cylinder concrete piles. These are examples of square concrete piles being driven. The one on the left is for a bridge, and the one on the right are fender piles for a dock. Cylinder piles are just what the name implies. They're actually normally cylindrically, they're centrifugally cast. That's what I want to say. They're centrifugally cast. They're pre-stressed and cylindrically cast, and as a result, they're fairly. The manufacture of these is fairly straightforward. You're seeing a few more places that do it. The first major application of concrete cylinder piles in the United States was the original Chesapeake Bay Bridge Tunnel between Virginia Beach and Cape Charles. And that was in the early 1960s. And all of the upgrades to that, I believe, have been set on. The first upgrade, I'm not sure about the one they're doing now, but the original upgrade, the widening, was done with cylindrical, as well with cylindrical concrete piles. They're very versatile. The only thing you got to watch for is sometimes you will have either hoop stress problems where you drive this and then you get an expansion due to Poisson's ratio, or water hammer where you actually are driving, the piles are below the surface of the water table, and you actually get water, as you impact the toe, a stress wave comes up and helps to crack the concrete pile. And there's a technical overview of them. This information is useful in trying to figure out where they're best applied. These are standard square and cylinder pile specifications. Again, I said, generally speaking, most cylinder piles are most are to this, and certainly most square. Now you're starting to see some variations. One of the problems concrete piles traditionally have had over the years is cutting them and splicing them. There are splicing systems, particularly with precast concrete piles, but also with pre-stressed as well. Cutting them is, but you have to, and when you have an uneven, which is almost inevitable, an uneven competent layer you're driving down to, you have situations where you need to cut off the pile at the top, and there are numerous ways of doing it. Composite piles, there are two definitions of that. It's one of those things where we use one term to apply to two different things, and it's confusing. One of them is meant to be pile types. For example, you have a concrete pile and you have an H-beam stinger stuck on the bottom of it. The other one is a plastic steel composite, and these are basically where you've got either a steel core and a plastic outside, very frequently made out of recycled materials, or some other configuration. I am personally surprised that, in fact, the feds sponsored an extensive study on this type of pile about 20 years ago, and there are some, but they've never really been accepted widely, as widely as you'd think they would be in the industry. Even though they don't have a lot of the handling issues with concrete piles can have to be handled with a great deal of care, and but and they don't create, have the environmental issues you have with wood piling. Still in all, these pilings have not gotten the acceptance that I would have thought they would have gotten. Mandrel bins, thin-shelled piles. Basically, these are fairly simple. The concept is simple. When we drive a pipe pile, we send, generally speaking, most closed-in, most piles in land applications are closed in, and they have when they're closed in, then they'll drive them and they'll fill them with concrete. And it's basically kind of like driving a hole in the ground for your concrete. Well, much of the wall thickness of those piles is due to having to get them in the ground. In other words, so that the pile won't basically collapse during installation. What would happen? They don't need to be that thick in order to pour concrete in them. Enter mandrel-driven piles. Basically, what you do is you take a very thin wall. Sometimes it's corrugated like a culvert. They look exactly like culverts, in fact, many times. Culverts, or there's step tapers where you've got this diameter and it goes down to this, and they're thin wall, and they put a mandrel in there. And the mandrel is a very heavy structure which transmits the impact force down to the, basically down to the pile without having to go through the pile. And for years, the most popular mandrel were your step taper mandrels. Raymond made very popular. And then you drive it. You check it to make sure that it hasn't collapsed during driving. Well, you drive it down. You pull the mandrel out, which is always an operation which brought out usually with Raymond particularly, brought out the destructive tendencies of their superintendents. And once they got out, they'd check it to make sure, then they'd go on. And they would put the rebar cage in, fill it with concrete, and they're done. Another type of pile, which you still see some, it was developed back in the 1920s in Belgium, the Frankie piles, is where you basically drive a tube in the ground, you hammer down, and then you hammer down the concrete into a bulb. What that does for you is that increases your toe resistance of the pile. You make a larger area, then the larger the toe area, the larger the resistance of the pile to loading. And Frankie piles are still used in some applications. This table shows you typical capacities and lengths of driven piles, and it's a nice guide to use when you're, particularly for land-based piles, when you're trying to figure out what pile do I use, what kind of loads will these piles take. This is a good general guide to that. We now turn to installation equipment for driven piles. We have to get them in the ground somehow. And I've touched on a few topics. Let's get into some more details. This is your basic pile driving system. This kind of presupposes a crane-based system. There are other systems. I'm going to show you some examples of those as we go along. There are different types of, let's start with impact hammers. Most piles are driven using impact, and there are some reasons for that. The other one would be vibratory hammers and pile jacking devices. I mentioned drop hammers. They've been around from the beginning of civilization. You simply raise the hoist and then let it drop to the impact of the pile top. It's simple, but it's very inefficient and slow. Sometimes it does its job too well. The high impact velocities, as one contractor in Florida put it, reduces piles to splinters before we try an air hammer. So, it has its downsides. Surprisingly enough, you still see them. For example, the widening of the bridge on, I believe it's Shalford Road Bridge over the South Chickamauga Creek. They actually use a drop hammer, which I was shocked. Usually in this area, diesel is your hammer of choice, but they used a drop hammer, which amazed me. Air hammer has been used, it says, since the 19th century, air or steam. They require little maintenance, and trust me, they don't get much. In fact, the reason, you ask, with the hydraulic hammers and whatnot, well, why do people still use this? Well, it's very simple. You can throw them out in the yard, and next time you need them, you just pick them up, pile of oil, and most of the time they'll just fire right up and keep going. They are long duration. When I say long duration, I mean in excess of 120 years, depending on what they've been driving over the years. The efficiency is variable due to the age. Diesel hammer, hydraulic hammer either runs or it doesn't, and usually when it runs, the efficiency is predictable. With air hammer, it will run under very poor circumstances, and therefore the efficiency will vary. They can either be single or double or differential acting. And by that I mean with a single acting hammer, the air steam is applied at the bottom, throws it up, drops it, and that's it. It's strictly the energy is equal to the weight of the striking parts times the stroke. That's it. With a differential or double acting hammer, you have downward, what we call downward assist, where it actually helps to push the hammer, the hammer downward, the impact. There are advantages and disadvantages to both. To get into that is a long business, and I'm not really, I won't take up time here to do that. Diesel hammers were developed in Germany between the world wars. In fact, I think I've seen photos of one out driving some of the resistance to the Allies when they, that resisted the Allies when they invaded the Normandy in 1944. And the Allies were not slow in recognizing the benefits of the technology. That took it back to the U.S., and there are diesel manufacturers in the United States. It's spread all over the world, basically. And they're light. They're basically a single piston diesel engine. You shoot fuel in, it explodes, it throws a ram up, it drops, it impacts, shoot more fuel, explodes, and so on. They can also be single or double acting. Well, double acting means a little different things with the diesel hammer than it does with an air hammer. This is the operating cycle, as you see. This is a 4-stage diagram. You can also reduce that to 3. The ram is actually has to be lifted up by a starting device, and then it lets go. It drops the first time. As it drops, the fuel is injected into the cylinder. The fuel hopefully explodes unless you've got very soft resistance. Diesels don't start very well in soft soils. And then it explodes and throws it back up. These are photos from downtown Chattanooga showing a diesel hammer driving sheet piling. And this is being used on sheet pile. You will notice the kind of scraggly tops, and I'll leave it to you to figure out why they don't have the sheets all driven to a nice even tops. Of course, they can just burn them off and they're done, but there's a reason for that, and I'll leave it to you to figure that out. But diesel hammers are very, very common for particularly driving sheeting. Diesels are very common for that, along with vibratories. And they're also used just about anything else. Hydraulic impact hammers, the first hydraulic impact hammer was a Raymond in the early 1960s. And it took a long time and a lot of investment of resources to get these accepted. They work basically like an air hammer, except they use hydraulic fluid. And they do, however, most of them have nice instrumentation, which tells you how much energy you're putting into the pile and all that good stuff, and how many blows you've done. And sometimes, there's sort of a pile driving log that they can develop. They are, it's personally, I don't think it's an optimal use of hydraulics, but they're popular. They've worked well when if they are. Some are more reliable than others. Reliability and maintenance have always been an issue with these. Like I said, some are better about that than others. Some of them are a little more expensive than others too. So hydraulic impact hammers are very much a part of the driven pile scene today. Vibratory hammers. At this point, we're talking about impact. Let's talk about vibratory hammers. The operating principle is interesting. You've got basically instead of beating on the pile, you have rotating weights, and as they rotate, they create a sinusoidal force. If they're synchronized, one way or the other, the side forces will cancel, and the horizontal forces will cancel, and the vertical forces will actually create a nice sinusoidal wave on the pile. Basically, it reduces, through that vibration, the resistance of the pile, and basically the entire system drops by its own weight. The Russians originally developed this in the 1940s, and the first application was on the Gorky hydroelectric development, which I think Gorky is now called Nizhny Novgorod. And it was an electric machine. There's talk about bringing electric machines back on the construction site, even though most American contractors are not real fond of electric machines on theirs. I actually saw this myself in what was then Leningrad, now St. Petersburg, of a Soviet electric machine driving U-shaped sheeting. We talked about U-shaped sheeting and sheet piling in what was then Leningrad, now St. Petersburg. And they actually plugged this thing into some kind of socket along the street to drive it, to actually use it. Once the Soviets first licensed the technology with the Japanese, and the Japanese had some interesting hammers, including the Uraga you're looking at. There were also, they went the other direction with it with Europe, in Europe. And these were all electric. In the earliest years, they were electric machines. It was not until the late 1960s that MKT up in New Jersey developed the first hydraulically driven vibratory hammer instead of using a hydraulic motor. That was more favorable to the American contractors and other manufacturers such as Foster and Ice and Ape and eventually Vulcan developed hydraulic vibrators, but the principle for all of them are the same. There are basically three types of these machines: the low, medium, and high frequency. You see there you've got the power pack for a hydraulic hammer, which is pretty good size for this pretty good size hydraulic hammer. I've got a whole web piece on this particular hammer in general, on how it on more of the fluid mechanics side of hydraulics. Low frequency vibrators were perfected the Russians and the Japanese, and they were primarily designed for very heavy piles, very large. And basically the way they worked was that they would, about 5 to 10 hertz, they literally pick up the pile and just drop it. In other words, it turns the entire pile into an impact hammer. And it was particularly useful for piles that needed to have a lot of tow resistance, and they needed help to get through that. This particular one, I actually saw one just outside of Moscow, had a dynamic force of 1,700 kilonewtons and eccentric moment of 510 kilogram meters, which is a pretty good size hammer. Most of what you see in the U.S. is medium, 10 to 30 hertz. It's the nice balance of frequency, eccentric moment, dynamic force. Most piles fall into that category. Larger vibratories do. And it was, and like I said, most of your machines made in the U.S. and used in the U.S. The only downside is in many cases these hammers are not the greatest when put up next to a neighboring structure. If you're out by yourself, pretty much you're okay. But if you're next to a neighboring structure, they're not. Sometimes the vibrations will affect those structures. One way to deal with that is high frequency vibrators. That particular hammer was one that I developed in the late 1980s. It ran at about 2,400 RPM, and it was designed to be, it's a non-resonant type of high frequency hammer, and it was designed to drive your lighter aluminum sheeting, as you see there at a Marine in Fort Pierce. It was also designed to be a lighter hammer, period. Easier to pick up, handle, and all that good stuff. And it worked pretty well. There are also your resonant hammers, which actually go back to the 60s, but only now I think they're really seeing any serious penetration of the market with them. They actually attempt to achieve resonance in the pile and or the soil and use that to assist the driving. A different ballgame altogether is pile jacking devices. They install the piling by pushing them to the soil without impact. For certain applications, this is a must, where you've got no vibrations can be tolerated. This is the good thing. The real disadvantage is, first of all, there are reasons why people use impact and vibration to assist, and that is that the forces for static jacking are just overwhelming. And the other one is that these, like your load test systems we're going to see, require a reaction system where you have to drive some stuff to start with and then clamp the hammer onto them, and then, or the jack, and then push it down against the reaction system. So that also limits this type of thing. But there are some applications where this is the thing to do. Most all impact hammers require driving accessories, and these are the basically mate the hammer. The hammer, there's no way to mate a hammer to every kind of pile that's ever driven. So you use a driving accessory to adapt it to one or the other. They hold the cushion material in place. You have hammer cushions in most cases. Not all hammers require hammer cushions. There are some that don't. And then the way the cap can influence the way that the energy is transmitted to the pile. Different types of cushion materials. I'm not going to get into that. There's what's best for a certain hammer. For one hammer, may not be good for your diesels, for example. Their cushions are fairly simple. Air hammer is a little more elaborate than that. Hammers generally, sometimes it's possible, and I think you saw that with the photo of the hydraulic hammer, to drive the piles, so to speak, wild, which basically means you don't have a leader system. Most of the time, you got to have a leader system, some type of guidance for the hammer as the pile goes down. And there are swinging leaders, such as the one on the right, which are good. They can be used with batter piles, and they are used with batter piles quite frequently. It's just that they're primarily developed for plumb, which is plumb means straight up and down. Or if you need something with better control over the hammer, you have fixed leaders. One interesting development we've seen in the last 6 or 8 years has been the development of an excavator mast-mounted hammer. As I said, most hammers are mounted on a crane. Excavator mast style mounting basically enables you to take just about everything but the main boom off the thing, put a mast on it, and use that to guide the hammer. An excavator operator an excavator in general is considerably less expensive to put in the field than a crane operator. And so therefore, for some types of driven piles, particularly the shorter ones, they're the deal, because they are limited in how long, they have some limitations versus crane systems and how long you can actually drive. But there are certain situations where excavator mast hammers are the way to go. They're a way of getting a pile rig without having it to do everything. In other words, an excavator is a very versatile piece of equipment for a contractor. And by the way, this is for larger excavators. You do not want to try to mount pile driving stuff on your smaller excavators. This is for your largest type of excavators. They're good for the excavators, but for obviously for the excavation, which is what they're developed for. But it can be used for other things, and to be able to use it for something else is obviously a value to the contractor. Sometimes piles need a little help getting in the ground, and the most common ways are pre-drilling and jetting. Pre-drilling and is a method. That has limitations where you basically drill a hole in the ground like with a continuous flat auger like you see here, and then you drive the pile into the hole. The problem with pre-drilling is the cavity expansion issue, and I'm going to talk about that more in detail next time when we get into actual capacity of piles. But obviously, for example, if you drill, there are times, like for example, if you got a nail that won't go in or a screw, particularly with screws, if you want a screw that goes in easier, you'll pre-drill a hole. You put the screw in. The trade-off of that is that there are two trade-offs. If you do put the hole in, the screw actually has less resistance to pull out. The other half of that is that if you don't put the hole in, the screw won't go in at all. So it's really kind of a trade-off, and many job specs have very fancy specs on how to deal with screws. How to deal with pre-drilling. What pre-drilling is permissible, what's, all that good stuff. Jetting is a whole different subject. Basically what it does is it puts water down either through a pile or down the side of a pile at very high pressure and loosens up the bond. Again, the same problem. If you jet a pile, it has, at least on a temporary basis, lower capacity because you've loosened up the bond between the soil and the pile. So you have to use jetting very judiciously, and you don't use it carelessly. You can, in some situations, jetting is the only way you're going to get a pile in. Jetting's effects, to some extent, reverse themselves. Okay, that pretty much completes my very brief overview. I'll mention one other thing about this particular presentation. This particular presentation, lecture, however you want to call it, actually dates from the early 1990s when I was still in the family business. I would go around different DOTs to present their, what pile driving was all about, and to familiarize themselves with this topic. And it's been a very useful. It was a very useful presentation. I think some of the people learned a lot from it, and some people slept through it. But in any event, that's where its root is, and I've been working on developing it ever since. So, in any event, we're going to get into more design-related things with driven piles. Until then, thanks for watching, and God bless.